Welcome to section 4 of RAG Mastery Playbook. In this section, we will explore what is a vector database, why are traditional databases not enough, what is actually stored inside a vector database, how can it search millions or even billions of embeddings in just milliseconds, what is similarity search, why do different vector databases exist, where does the vector database fit into the complete RAG pipeline? Let's begin. So, what it is a vector database? Let's first think about a simple example. Imagine a massive library containing millions of books. We walk in and ask the librarian, "I'm looking for a quiet story about finding yourself." Does the librarian start reading every single book one by one? Of course not. That would take years. Instead, the books have already been organized and catalogued according to their themes, subjects, and characteristics. The librarian simply knows how to navigate that organization, quickly guide you with the most relevant books. A vector database works kind of in a similar way. In the previous video, we have learned that every chunk of text is converted into an embedding, a numerical representation of its meaning. For example, if the original text is employees are eligible for paid leave under certain condition, after an embedding model processes it, it may become something like this, like 0.21 minus 0.45, 0.72, 0.12, so on so forth. In reality, an embed usually contains hundreds or even thousands of numbers, but the idea is exactly same. Now imagine the system stores something like this. Employees are eligible for paid leave and the relevant embedding is also stored there. The original text still exists. The vector database stores the embedding along with a reference back to that original chunk. So it always knows that which document that meaning belongs to. Instead of searching words directly, it searches those vectors. Before we go further, let's understand one important term, vector. Now, what is a vector? A vector is not a word or a sentence. It is simply a list of numbers that mathematically represents the meaning of that piece of text. For example, after an embedding model processes the sentence, employees are eligible for paid leave, it may generate something like 0.21 minus 0.45, 0.72, 0.13 and it goes. These numbers may look very meaningless to us, but to an AI system, they capture the meaning of that sentence. In simple words, a vector is AI's mathematical representation of meaning. You can think of these vectors as the GPS coordinate of that meaning rather than the words themselves. So, instead of asking which document contains exactly these words, the system asks which stored meanings are the closest to the meaning of the user question. So, its job is to organize millions or even billions of these vectors and quickly find the ones that are most semantically similar. This is one of the most common question people ask when they first learn about vector database. If embeddings are just list of numbers, then why can't we simply store them in a traditional SQL or relational database? Why do we need an entirely different database called a vector database? At first glance, this sounds like a perfectly reasonable question. After all, SQL databases already store numbers, text, dates, and millions of records. So why can't they simply store embeddings as well? The answer is actually quite interesting. We certainly can store embeddings in a traditional database. The real challenge is not storing them. The real challenge is finding the most similar meanings quickly and efficiently. Let's understand this with a simple example. Imagine a library containing 10 million books. Now suppose you walk in and ask the librarian, "I'm looking for a book that feels like a story about finding yourself." Notice something important. You did not ask for a book containing the exact words finding yourself. Instead, you asked for a book with a similar meaning or feeling. That is a very different type of search. Now let's compare this with how a traditional SQL database works. A traditional SQL or relational database is excellent when the question is precise. For example, find employee ID equal to 1025, find department equal to finance, find salary greater than 1 lakh, find all books where author equal to J.K. Rowling. These all are exact conditions. SQL databases are designed and optimized for exact matching and structured filtering. They are incredibly powerful for this purpose. But AI system usually ask a different kind of question. Instead of asking find this exact word, they are asking find meanings that are most similar to this meaning. Now this is a complete different problem. Imagine there are 100 million embeddings stored. Each embedding itself contains hundreds or even thousands of numbers. Suppose a user asks a question. The system first converts that question into another embedding. Now it has to find which stored embedding is most similar. If traditional database simply compared that embedding against every stored embedding one by one, the computation would become enormous and the search would be far too slow. It would be like asking a librarian to open and inspect every one of the 10 million books before recommending one. Clearly, that is not practical. This is exactly why vector databases were created. Their purpose is not merely to store embeddings, but their purpose is to organize embeddings in a way that allows the system to rapidly identify the nearest or most semantically similar vectors without performing a full comparison against every stored vector. They are specifically optimized for similarity search at massive scale. Whether there are millions or even billions of embeddings, they are designed to retrieve the most relevant one in just milliseconds. So the simple takeaway is a traditional SQL or relational database answer that question, does this record exactly match my condition? Whereas a vector database answers the question, which stored meanings are most similar to the meaning of my question. That's the fundamental difference. And that is why modern RAG systems use vector databases instead of relying solely on traditional SQL or relational database. Now, an even more interesting question naturally arises. Let's understand that next. Now that we understand what a vector database is, another important question naturally arises. What exactly is stored inside a vector database? Many people assume that a vector database stores only embeddings, but in reality, it typically stores three things. First, the embedding vector itself. As we have learned earlier, an embedding is a numerical representation of meaning. For example, suppose we have the sentence, employees are eligible for paid leave under certain condition. After the embedding model processes this text, this may generate something like 0.21 minus 0.45, 0.72, 0.13 and list continues. The actual embedding usually contains hundreds or even thousands of numbers, but the idea is the same. The embedding is the first thing which will be stored inside the vector database. Second, the original text or a reference to the original chunk. The vector itself is useful for searching, but it is not useful to a human. When the system finds a relevant vector, it must be able to retrieve the actual text that produced that vector. That is why the original chunk or a reference to it is also stored. Now third is metadata. Metadata is simply additional information about that content. For example, document ID, chunk ID, file name, department, category, or any other information that may help organize and filter the data. So internally, a vector database might contain something like this. First, the embedding, the numbers. Original chunk, employees are eligible for the paid leave under certain condition. Then the metadata, HR policy chunk 27, document 104. So simple takeaway from this example we can draw is a vector database does not just store meaning, it stores three things: the embedding that represents the meaning, the original content that generated that meaning, and the metadata that helps identify and organize that content. Together, this allows AI system to retrieve the right information when it is needed. Now that we know what is stored inside a vector database, another important question naturally arises. How can it search millions or even billions of embeddings in just few milliseconds? Let's look at a simple real-world example. Suppose a company has hundreds of HR policy documents. After chunking and embedding, the vector database now contains thousands of embeddings. Now imagine, an employee asks, how many days in advance should I apply for leave? The first thing in the system does is to convert this question into an embedding. The vector database then receives that embedding and begins searching for similar meanings. One possible approach would be to compare the user embedding against every stored embedding one by one. This would work, but as the number of embeddings grows into millions, the search would become increasingly slow and expensive. So, instead of a vector database organizes embeddings so that the similar meanings are located close to one another. For example, embeddings related to leave policies may be grouped near other leave-related content. Payroll-related embeddings will be located near payroll information. Benefits-related embeddings may be located near benefit information. When the user now asks a question about leave, the vector database can quickly narrow its search to the area that contains leave-related meanings. Instead of searching the entire database, it searches only a much smaller set of highly relevant candidates. Among those candidates, it may find chunks such as employees are eligible for paid leave. Leave request must be submitted at least 5 days in advance. Manager approved leave request. The database identifies the most relevant chunk and returns it to the AI system. The AI model can then use this information to generate the final answer. So the simple takeaway is a vector database is fast not because it searches everything, but it is fast because it intelligently organizes the embeddings and quickly focuses on the most relevant areas of meaning. That is how modern AI system can retrieve relevant information from millions or billions of embeddings in just few milliseconds. Now that we understand how a vector database can search millions or even billions of embeddings efficiently, another important question naturally arises. How does the database decide which embeddings are actually similar? This process is called similarity search. Let's continue with the same HR policy example. Suppose an employee asks, how many days in advance should I apply for leave? As before, the system converts this question into an embedding. This vector database then begins its search for embeddings that are closest in meaning to the user question. Now notice something important here. The database is not searching for the exact words apply for leave. Instead, it is searching for embeddings that represent similar meanings. This is a semantic search rather than a keyword search. Now imagine the database contains following chunk. Chunk A, employees are eligible for paid leave. Chunk B, employees' request must be submitted at least 5 days in advance. And chunk C, managers approve annual leave request. Although the three chunks are related to leave policies, they are not equally relevant to users' question. The question specifically is asking how many days in advance should I apply for leave. Among these available chunks, chunk B is clearly the closest match. Similarity search works by comparing the query embedding with stored embeddings and calculating how close they are in vector space. Now think, embeddings that are closer together are usually considered more similar in meaning. Embeddings that are further apart are considered less related. The database may now assign similarity scores such as chunk B is 95% similar, chunk C is 88% similar, chunk A is 81% similar. The exact numbers are not important. What matters is that ranking. So the most relevant chunks receive the highest similarity scores. Instead of returning every matching chunk, the database usually returns only the top results. For example, it may return the top 3 most similar chunks from millions of stored embeddings. AI model then receives those retrieved chunks and uses them to generate the final answer. Without similarity search, the system would have no reliable way to determine which information is most relevant to the user question. So simple takeaway is this: the similarity search is the process of finding the stored embeddings whose meaning are closest to the meaning of the user question. It is the fundamental capability that allows vector database to retrieve relevant information for modern RAG systems. At this point, you might be wondering something. If all vector databases store embeddings and perform similarity search, why do we have so many different products such as Pinecone, Milvus, Weaviate, Chroma, FAISS, Qdrant? The answer is simple. They all solve the same fundamental problem, but they are optimized for different use cases. Think about relational database. We have MySQL, Oracle, SQL Server, all store relational data. But yet, organizations choose different databases based on their requirements. Vector databases are no different. For example, some vector databases are designed for massive cloud scale deployments handling billions of embeddings. Others are optimized for local development, experimentation, and smaller application. Some focus on simplicity and ease of use, where others focus on performance, scalability, filtering capabilities, or enterprise grade features. For example, FAISS is a popular open source library widely used for high performance similarity search. Chroma is often used for local development and prototyping. Pinecone provides a fully managed cloud service. Milvus and Weaviate are designed for large scale production workloads. Qdrant is known for combining vector search with rich filtering and metadata capabilities. The important point is that although these systems differ in implementation and features, the core concepts always remain exactly the same. They all store embeddings, organize them efficiently, and perform similarity search to retrieve relevant information. So simple takeaway is different vector database exist because different applications have different requirements, but they all serve the same fundamental purpose: efficient storage and retrieval of embeddings. Now that we understand what a vector database is and how it works, let's see where it fits into the complete retrieval-augmented generation or RAG pipeline. A vector database is not the entire RAG system. It is one of the most important components within a larger workflow. Let's use a simple example. Suppose an organization has thousands of HR policies, employee handbooks, internal documents, etc. The first step is data ingestion. The documents are collected and prepared for processing. Next, the documents are split into smaller chunks. Each chunk then converted into an embedding using an embedding model. These embeddings, along with the original text and the metadata, are stored inside the vector database. This completes the indexing phase. Now imagine an employee asks, "How many days in advance should I apply for leave?" The question is first converted into an embedding using the same embedding model. That query embedding is then sent to vector database. The vector database performs similarity search and retrieves the most relevant chunks. Those retrieved chunks are then passed to large language model. The language model uses the retrieved information as context and generates the final answer. Notice something important. The vector database does not generate the answer. The large language model does not search the document directly. The vector database retrieves the relevant information and the large language model uses that information to create the response. So the simple takeaway is, in a RAG system, the vector database acts as the retrieval engine that connects enterprise knowledge with the AI model, helping the system produce accurate and context-aware answer. And with that, we have completed our deep dive into vector databases. By now, you should have a solid understanding of one of the most important building block of modern AI and retrieval-augmented generation system. In the next video, we are planning to take a deep dive into top K retrieval and ranking and explore how AI systems decide which retrieved information is most relevant. Thank you for watching. If you found this video useful, please consider liking and subscribing to this channel. Until next time, this is EdgeTalks, clarity that moves with you.